Guys, how are you? Thank you for being here today. I am Engineer Kashif and here today to talk to you about ideal and actual basic Rankine cycle with operation characteristics. Now, Rankine cycle is the basic cycle for steam turbine power plant. In ideal Rankine cycle, does not involve any internal irreversibility. In reversibility, you can say there is no losses and consist of the following process. You can say there are four process. If we discuss in next picture, you can see this is a turbine portion, this is condenser portion, and this is feed water pump, and this is boiler portion. If we categorized the portion, first one is turbine. Suppose that this point is 1 and this point is 2. This point is 1 and this point is 2. 1 to 2 process point, a centropic expansion of superheated steam. In this process involves a centropic expansion of the superheated steam. Next, process 2, number 2 to number 3. In this portion, constant pressure heat rejection, you can say barometric process involves. Number 3, process 3 to 4, pressurization of saturated liquid in pump. Next step, 4 to 1 constant pressure heating process. But if we subcategorized the portion of boiler, suppose there is some portion, first one is economizer, second one is steam drum, and third one is superheated. And 4 to 5, 5 to 6, 6 to 1 in ideal cycle. 4 to 5 constant pressure heating in economizer, 5 to 6 constant pressure heating in steam drum, and 6 to 1 constant pressure superheating of saturated steam to superheated steam. In process 1 to 2, mechanical work is obtained. Mechanical work is obtained by expanding superheated steam in turbine portion to make process adiabatic. Process speed increase and system is made insulated. Normally absorbed material is used on turbine cover for insulation process is adiabatic, having bearing friction and viscous friction, which is negligible. State 2, this one, state 2 is in wet vapor state and dryness friction is kept more than 0.8 because lesser is the dryness friction, more will be coefficient of friction, leading to lesser efficiency. Moisture content also causes the rusting of turbine blades. State 2 to 3 in the condenser vapors are condensed using heat exchangers. Basic purpose of condensation is to reduce the steam volume since it is quite difficult to take large volume. So condensation reduced pump work input considerably. Because of condensation, condenser pressure is easily maintained at about 1/10 of atmospheric pressure. Water leaves condenser in saturated liquid state. So state 3 to 4, saturated liquid from the condenser is pressurized in the pump to the pressure at which heat addition process will take place. Ideally, this process is asentropic. You can say the component involved in steam turbine, power plant or steam turbine, condenser, pump and boiler, all of these are considered to be controlled volume. We will apply the steady state equation, a flow process on each component. You can say internal energy, yani you can say energy equation for the steam turbine for unit mass flow rate. Suppose that M is to 1, so Q is to 0 for asentropic process. You can say reversible adiabatic process. So Q is 0 since the process is reversible adiabatic. If we neglect change in potential energy and kinetic energy, next in process 4 to 5, preheating at pressurized liquid from pump is carried out using economizer and sometimes with gases from preheating while feed water heater. Use extracted steam from intermediate state of turbine. The most recommendation number of feed water heater are 2. Next state is process 5 to 6. 5 steam drum and after 6. At constant pressure in boiler, saturated liquid is heated to convert into saturated vapor by adding latent heat of vaporations. Pressure remains constant in the boiler. Last is 6 to 1. 6 to 1 steam, saturated steam is converted into superheated steam by passing it through coils which are very close to the flame, but flame does not touch these coils. Again, pressure remains constant. The superheated steam is fed to turbine, completing the cycle. If we consider the mathematical equations, Rankine cycle efficiency W over Q. W is the work done and Q1 is heat absorbed by heat engine from boiler. W is total work done. So W1 work done of turbine. You can say mechanical output at turbine minus W2 mechanical work input to the pump into the pump. Total work done of turbine minus input work done to pump is equal to W1 minus 2 over Q1. Q1 is heat absorbed by heat engine from boiler. So this is the ideal Rankine cycles. In TS diagram, you can see Q1 is the boiler heat work, W1 is the work done of turbine, W2 is the work done of pump, and Q rejection of heat in condenser. So this is the TS diagram and process. This one is 1, 1, 2, 3, 4, 5, 6 and 1. 1, 2, 3, 4, 5, 6, 1. Now you can say Q1 heat rejected by heat engine to condenser. If we categorize the latent heat, you can say enthalpy. We simply write on the Q2 is equal to H2 minus H3. H through H2 minus H3. And Q1 Q1, heat absorbed by heat engine from boiler. This one, Q1. Q1, H1, H1 enthalpy of at this point, and minus H1 minus H4. This one. 1, 2, 3, 4. This one. So Q1 is equal to H1 minus H4. You can say heat supplied to the boiler. But Q2, heat rejected by condenser to cooling purpose. You can say H2O. So W net, W turbine, W1 is the W turbine, work done of turbine, minus work done of pump. So Rankine ideal efficiency in enthalpy form, H1 minus H2 minus H4 minus H3 over H1 minus H4. Ideal Rankine cycle is one in which all processes are assumed to be reversible, not irreversible. Reversible. Let us move to actual Rankine cycles. This one is actual Rankine. One cycle. In TS diagram, this deviation of line from 1 to 2 is the actual, and 3 to 4 pink line is also deviations. Simply, in ideal Rankine cycle, the process taking place in turbine, condenser, pump, and boiler are assumed to be reversible. We are neglecting the friction losses, viscous losses, pressure drop, and considerable heat transfer when these losses will be incorporated in the thermodynamic cycle. We will get actual Rankine cycle. The thermal efficiency of ideal Rankine cycle is higher as compared to actual Rankine cycle. On TS diagram, the actual Rankine cycle and ideal Rankine cycle are shown. Deviation in steam turbine. Ideally, there is asentropic expansion of superheated steam in the turbine from 1 to 2. Actually, there is expansion of superheated steam from condition 1 dash to 2 dash. This deviation is due to undesirable heat loss from turbine to the environment on surroundings, and also there are friction losses